Hello everyone, welcome to lecture 18 of the online course on modern display technologies, flat panel display. In this lecture, we will continue our discussion on the electric field effects on liquid crystal displays. So this will be the lecture outline. We have been discussing the effects of electric field on liquid crystals. So in this lecture, we'll focus on ferroelectric liquid crystal. We'll talk about the symmetry and polarization, tilt angle and polarization, and then we'll move on to surface stabilized ferroelectric liquid crystals, or SSFLCs in short, and the electroclinic effect in chiral smectic liquid crystals. So let's look into the ferroelectric liquid crystals here. So the first question here we'll be addressing is the symmetry analysis, and we'll understand why pneumatics cannot be ferroelectric. Okay, so this is how pneumatic liquid crystals look like. Okay, so uniform pneumatic liquid crystals cannot show spontaneous polarization due to d infinity h symmetry. So this is d infinity h symmetry is basically dihedral infinity point group. So it is basically a high symmetry point group in chemistry and physics, especially assigned to linear molecules that possess a center of inversion. So it represents the highest possible rotational and reflective symmetry for 3D linear systems where both ends of the molecules are identical. So here what happens for rod-like molecules, polarization along the director n is not possible because n and minus n are basically equivalent, right? So next we see the cholesteric, or that is basically the chiral pneumatic liquid crystals. They basically contain chiral molecules, but here also their D2 symmetry prevents the ferroelectricity. So here what happens, the twofold rotational symmetry in cholesteric liquid crystals basically rules out both parallel and perpendicular spontaneous polarization. Now we can focus on the smectic A type, where you see the plane wise the molecules are aligned. Okay, so they are basically having layers. So smectic A liquid crystals have layered structures with director n perpendicular to these smectic layers. So smectic A phase cannot show instantaneous polarization even for chiral molecules due to continuous rotational symmetry around n cap. So they have this rotational symmetry, so they can't show spontaneous polarization. Now what about smectic C? So in smectic C kind of crystals, you basically have a tilted director n with respect to the layer normal A. So layer normal will be along this. Okay, so this will be the direction of layer normal, and this is your n, that is the director. So ordinary smectic C has C to H symmetry that also prevents spontaneous polarization. However, if you take chiral smectic C, or that is called C star, okay, so in this kind of liquid crystal, which is something like this, okay, here you can see the molecular chirality basically removes the reflection symmetry. Okay, so these are the different layers, okay, and there is chirality in that. So this is the helix axis. So this is the schematic diagram of the chiral smectic C. Now what happens here, due to C2 symmetry, spontaneous polarization becomes possible along that direction perpendicular to both N and A. Okay, so in chiral smectic C or C star, the director n, that vector is basically tilted within each layer and twists from layer to layer. So in that case, net polarization will arise from non-cancelling lateral dipoles of the chiral tilted molecules. So here you can see that these molecules are basically tilted, and you can see there are spontaneous polarization, right? Now, if the tilt angle, that is this theta, that becomes 0, in that case all these molecules will become straight, okay, they will be vertical. So the structure basically behaves like smectic A, and the polarization will cancel. So in smectic C liquid crystal, when these molecules are racemic mixture, that means you basically have equal amount of left and right handed molecules, okay. So in such racemic smectic C mixtures, you will see that the opposite dipoles from the left and the right handed molecules also can cancel out each other, okay. So the ferroelectricity in liquid crystals basically requires both molecular chirality as well as some tilted smectic C ordering. So what we understood, that only chiral smectic C, that is C star liquid crystal, can exhibit spontaneous polarization because their reduced symmetry will allow a unique polar direction perpendicular to both the layer normal as well as the director. So here is a summary and comparison of the symmetry and the polarization for different types of liquid crystal phase. So nematic, this is the symmetric group. Chirality is not needed, but you don't get any spontaneous polarization also, so you get no ferroelectricity. Cholesteric is D2 symmetry, chirality is there, but polarization, spontaneous polarization is again 0, so is the ferroelectricity. Smectic A, the symmetric group can be D infinity H or D infinity. Chirality is not a requirement here, it can be achiral or achiral, but it doesn't make any difference. The spontaneous polarization will be 0 and ferroelectricity also not there. Smectic C, when the things are achiral, okay, polarization is 0, ferroelectricity is not there, but when there is chirality and C2 symmetry in the smectic C, that becomes smectic C star. There you have spontaneous polarization, which is A cross N. So your polarization will be, spontaneous polarization will be parallel to that, and then you have also ferroelectricity, right? So now let us understand the tilt angle and the spontaneous polarization in more details for smectic C star, okay. So there is temperature dependence of tilt angle in this smectic C star kind of liquid crystals. We have seen in smectic A phase tilt angle theta equals 0, and smectic C phase it is tilted, so your director is basically tilted with respect to the layer normal. So whenever the liquid crystal is transitioning from smectic A to smectic C, it is a second order phase transition, and the tilt angle theta basically acts as the order parameter of the transition. Now when this transition is taking place, there is a transition temperature that triggers this. So below the transition temperature Tc, the tilt angle gradually increases as the temperature decreases, okay. And near Tc, the free energy density can be written using the Landau expression, and you can write F equals F naught plus A half A T minus Tc theta square plus half B theta to the power 4. So here F is basically the free energy density, F naught is the reference free energy density, A and B are the positive temperature independent coefficients, Tc is basically the smectic A to smectic C transition temperature, and theta you all know that is basically the tilt angle, okay. Now how do you find the equilibrium tilt angle? That can be obtained by minimizing the free energy. So you minimize this free energy by taking the derivative of F with respect to theta and you equate it to 0. So that gives you dou F by dou theta equals A T minus Tc into theta plus B theta cube equals 0. So you can find solutions for theta in this case below Tc. Whenever the T is less than Tc, the stable solution is theta equals square root of A by B times square root of Tc minus T. So this relationship is also valid for chiral, smectic, C-star kind of liquid crystals. Therefore, the tilt angle increases continuously below Tc, confirming a second order transition behavior. Now, what is the relationship between this tilt angle and the spontaneous polarization? So, you have seen that in smectic A, the director N is basically normal to the layers and molecular rotation is unbiased. Okay. Now, if the molecules have lateral dipoles, they will be equally distributed in all the directions perpendicular to N. So that is the reason why smectic A does not show any kind of spontaneous polarization. However, in smectic C, your tilt angle becomes non-zero. So in that case, the rotational symmetry around the molecular axis is now broken. However, if the molecules themselves are achiral, then the dipoles which are basically pointing out and pointing into the NA kind of plane, they will cancel out each other. So you are having smectic C with achiral molecules, you basically don't see any spontaneous polarization. Now only in the case of chiral smectic C star kind of phase, you will see the reflection symmetry about the NA plane that is broken. So NA plane is understood, that is N is the director, A is the layer normal, the plane they are in. Okay, so the reflection symmetry about that plane will be broken. So in that case, net spontaneous polarization will become possible. That will be in the perpendicular direction to this particular NA plane. So the direction of spontaneous polarization basically depends on molecular chirality and also the molecular structure. So what if the tilt angle changes from theta to minus theta? What will happen? The spontaneous polarization will also change its direction. So you can therefore say that spontaneous polarization PS must be an odd function of theta. So here this small c is the polarization tilt coupling constant, which has a unit of Coulomb per meter square into radian. So larger tilt angle theta can produce stronger spontaneous polarization. That it is very obvious from this particular equation. Now the ferroelectricity in smectic C star basically arises from the coupling between the molecular chirality, director tilt and lateral dipole alignment. So with that, now let us move on to the surface stabilized FLC device. So in 1980, Clark and Legawal, they basically published a groundbreaking paper where they talked about this work of surface stabilized ferroelectric liquid crystal or SSFLC. So this basically could revolutionize flat panel displays, where they achieved switching speeds which are thousands of times faster than the existing technology. So let us see how they actually propose this FLC device. So what are the problem with the bulk smectic C star? We have seen that in thick cells, the helical twist of the director N from layer to layer will produce macroscopic optical axis that rotates with position. So if you take average, they will basically average out to optically isotropic. So in that case, the spontaneous polarization will also average out to 0. Now the proposed solution of surface stabilized FLC device was something like that. If the cell gap H is smaller than the helical pitch P, in that case the parallel anchoring alignment layer would suppress and unwind the helix. Okay. So in that case, the bookshelf geometry with smectic layers perpendicular to substrates and the helical axis will be parallel to the substrates. Okay. So let us see the schematic diagram of this one, which is the book cell structure of the surface stabilized ferroelectric liquid crystal display. So in this first case, the director is along the direction A1 when the applied field is in this particular direction. Here when you change the field to downward, the director basically changed to A2. So this is how the director angle has changed. Okay, so this is basically the direction of the polarizer and the analyzers, right? And this basically shows the cone axis. So this is basically the tilt is theta, tilt angle. So this will be the cone axis. So this is your polarizer, this is the analyzer. Okay, and you can basically see the director angle when the electric field is changing. So there are basically two stable states, okay, like this. So with the helix unwound, the director is confined to the smectic cone, and only two orientations, one is this A1, another is this A2, which are basically separated by 2 theta. These two are compatible with the surface anchoring, and these are selected by applying DC field polarity. So when you say A1, this particular A1 state, here the field is in plus Z direction, right? This is the Z direction, this is your electric field direction. So the spontaneous polarization also points up, that is parallel to the field, and that minimizes the energy. So once switched, the state is basically retained after the field is removed, because the energy barrier between the A1 and A2 will basically prevent the spontaneous switching. So you are basically getting true bistability. The another state is this A2 state, when the field is in the minus Z direction. So here the spontaneous polarization also points downwards, but the director has basically now rotated by 2 theta in the same cone from this A1. Okay, earlier A1 was here, so from that you have gone to 2 theta, right? And the cone angle is nothing but the tilt angle of this smectic C crystal. So let us see the optical operation and the transmittance for this kind of SSFLC displays. So we have seen that in an SSFLC display, the polarizer is aligned parallel to one stable state A1. Okay, so it's like this, and the analyzer is basically placed perpendicular to the polarizer. So when liquid crystal is in state A1, incident line polarization remains parallel to the director N, and when the light is coming out of the cell, its polarization is basically perpendicular to the analyzer, and that is why the display will appear black or is in dark state. And then when the liquid crystal switches to state A2, the incident polarization will make an angle 2 theta with the director. During the propagation through this liquid crystal cell, the polarization rotates and light is transmitted. So you can write the display transmittance T as sine square 4 theta into sine square pi delta n h by lambda. So delta n is basically the birefringence, h is the cell thickness, and lambda is the wavelength. So this is a very standard formula for wave plate between the cross polarizer placed at 2 theta angle. So when you get maximum transmittance, that is 1 or 100%, that will come when you get 2 theta equals pi by 4, that means theta equals 22.5 degree, and the retardation, that is delta n into h, that will be half wavelength, that is lambda by 2. So standard FLC design basically targets this simultaneously, that allows one to select liquid crystal tilt angle as well as the cell gap h. So for ferroelectric liquid crystals, electric energy density under the applied electric field E can be written as U equals minus PS into E. So typical spontaneous polarization, the values can be something like PS equals 100 nanocoulomb per centimeter square, or you can write it as 10 to the minus 3 coulomb per meter square. And when you have an applied electric field, something like E equals 1 volt per micrometer, that is 10 to the power 6 volt per meter, and you consider the polarization to happen in the parallel direction to the electric field, and PS is parallel to E. Electric field density becomes modulus of U, which is modulus of minus PS dot E, and you can see that that comes out to be around 10 cube joule per meter square. So this strong coupling between the spontaneous polarization and the electric field basically gives ferroelectric liquid crystal devices very fast switching speed. So that is the reason of this fast switching that is achieved here. Now let us look into the Goldstone mode. So in SSFLC, the detector rotates around the cone, and in this mode the azimuthal angle phi, okay, so this is the azimuthal angle on the cone, is the relevant dynamic variable that is shown in this figure, and the cone half angle is basically theta, that is nothing but the liquid crystal tilt angle. So what is the electric torque during switching? You can calculate that as tau E equals PS cross E. So that is basically PS E sin phi x cap. Viscous torque can be written as gamma V, which is minus gamma sin square theta dou phi dot T x cap, and gamma is basically the rotational viscosity constant. Now the torque balance gives the dynamic equation E sin phi minus gamma sin square theta into this term, that is dou phi dot T will be equal to 0. So in this equation the solution for phi t will be 2 tan inverse of 10 phi naught by 2, it is about T by gamma sin square theta by PS into E. So what do you see here? The response time tau is basically gamma sin square divided by PS into E. Now if you plug in those values that you have seen earlier, okay, say you consider PS equals 10 square nanocoulomb per centimeter square, E equals 1 volt per micrometer, gamma equals 0.1 Poisson, you will get, and theta equals 22.5 degree, you will get tau equals 10 microsecond. That means you get microsecond scale switching of these liquid crystals. So this first switching mainly occurs due to strong polarization field coupling. Second, small cone angle theta, that means small rotational displacement, and third thing is that the response time is inversely proportional to the electric field. So what are the advantages and limitations of this SSFLC devices? The first advantage, as you can understand, the first switching with switching time in the range of 10 microsecond as compared to the twisted pneumatic LCTs which have switching time of around 10 millisecond. So this allows very high frame rate sequential color displays without color breakup artifacts, and the time sequential RGB illumination is feasible at 180 Hertz. Second advantage is that the strong electric field coupling through spontaneous polarization. The third advantage is bistability. So once switched, the detector basically remains in state without holding voltage. So this enables passive matrix, that's multiplexed kind of displays without thin film transistors. So this allows you to reduce the power consumption in static image applications, something like e-readers and signage. However, all is not good in this. There are some disadvantages, something like the grayscale difficulty. So the bistability basically means binary states A1 and A2 are stable. Analog grayscale requires spatial, that is half tone or temporal dithering. So you basically require very complex driving schemes. And the second disadvantage is the alignment uniformity. So achieving uniform bookshelf geometry over large area is very challenging, and schematic layers tend to form chevron defects, that's like tilted bookshelf or other textures. So the surface alignment requirement is very precise, and The third disadvantage is the shock sensitivity. This smectic C chiral type liquid crystals is a layered phase, so any mechanical shock can also disrupt the smectic layer structure. So recovery from the shock disturbed state may require thermal cycling back through the smectic A or isotropic phase. So these are the disadvantages along with the high switching speed that you can get from SS-FLC device. So with that, we conclude our lecture here. If you have got any query regarding this lecture, you can drop an email to this email address mentioning the course name on the subject line. Thank you.